Good evening, ma'am. Am I audible to you? Good evening, ma'am. Am I audible to you? Good evening, ma'am. Am I audible to you? Is everything clear?
Good evening, sir. Sir, your voice is very low, sir.
Yeah, that's why I wanted to check, ma'am. Please wait, let me check.
Yeah, sir.
Okay. Is it okay, ma'am, now?
No, sir, the same way.
Okay, ma'am. Let me check now. Good evening, students. Is everything clear now? My audio? Is it clear to you, students? My audio? Are you able to hear me?
Sir,
Yes.
sir, can't
Yeah.
hear you properly, sir.
Okay. So that's why I have rejoined the meeting, but still the problem is there, I think.
Sir, now I can hear, sir.
Now
Sir,
you
it's
can
okay,
hear
sir,
that.
now.
Okay, ma'am. Okay. Thank you so much. Thank you so much. Okay. Good evening, students. So,
Good evening, sir.
yeah,
Good
before starting today's discussion, I wanted to discuss the solution for the 15th problem. Okay, problem number 15 in the test which I had given you few weeks ago, I think, on electric charges and field. Okay, I gave you a test containing 15 questions. So in that test, I am going to discuss the solution for question number 15. Now I will display the question to you by sharing my screen. So let us see what they have asked in the question. Then we shall proceed for the solution. So here is the question. Are you able to see the screen? I have shared my screen now. Are you able to see that?
Yes, sir.
Thank you. Thank you. So this is the question to you. 3 point charges plus q, minus 2q and plus q are placed at points x equal to 0, y equal to a, z equal to 0. X equal to 0, comma y equal to 0, comma z equal to 0 and x equal to a, comma y equal to 0, comma z equal to 0 respectively. The magnitude and direction of electric dipole moment vector of this charge assembly are. So they have given you 4 options, and what you have to do is you have to find out the magnitude and direction of the electric dipole moment vector due to this charge assembly. Charge assembly means they have mentioned the point charges plus q, minus 2q and plus q. So these charges are placed at different points, and they have given the coordinates of the points too, and due to the charge assembly you will be getting the electric dipole moment, okay, the net electric dipole moment, and due to this charge assembly you have to find out the magnitude and direction of the dipole moment. So that we have to find out. I think you all understood the question very well, okay. So now we will be discussing the solution for this problem. So for that I will be opening the whiteboard now. So first of all, what we have to do is we have to draw the diagram showing the different charges. Okay, as it has been given in the question, we have to first draw the diagram. After that, we can proceed. Okay. So first of all, we have to consider the Cartesian coordinate system. Okay. Cartesian coordinate system we have to consider, because in the question itself they have clearly given the hint that it is the Cartesian coordinate system. So now we have to proceed accordingly. Okay. So in the diagram, I am actually showing you the 3 axes. Okay. So this is actually your y axis, and this is actually your x axis, and this green color one, it is your z axis. Okay, so x, y and z, and they have given that the charges are placed at different points. Okay, so here you are having a plus q charge. Okay, and they have given you the coordinates of this as well. So that is 0, comma a, comma 0. Okay, and another charge that is placed at a, comma 0, comma 0. So that is, let us consider here, that is also plus q. Okay, so this is placed at the point a, comma 0, comma 0, and they have mentioned that the charge minus 2q is present at the origin. So minus 2q is present here at the origin, 0, comma 0, comma 0. Okay, so now we have to find out the net electric dipole moment and the direction of the net electric dipole moment as well. We need to find out. So here you see you have a minus 2q here and you have plus q. Here you have plus q. So for this charge you have to consider that this minus 2q, you can separate it into two charges. Okay, you can separate this into two charges. Please wait, I'll be back. Yes, students, sorry for the interruption. So here you see the different charges have been placed at the different points, and this minus 2q, it can be considered as two minus q charges kept at this point. Okay, one minus q charge here and another minus q charge here. So this minus 2q charge can be considered to be a collection of two minus q charges. So one minus q charge here and another minus q charge at the same place. So in that way, what you can consider is you have two electric dipoles here. Okay, so one dipole consisting of this plus q and minus q here, and another electric dipole consisting of minus q and plus q here. Okay, so what I am doing is I am considering this minus 2q as the collection of two minus q charges kept at this point. After that, I am considering two electric dipoles. So one dipole consisting of this plus q and minus q here, and another dipole consisting of this minus q and this plus q here. Okay, so in this way you are having two electric dipoles here, and there will be two dipole moment as well. So the net dipole moment, how can we calculate? So the net dipole moment can be calculated by, since this is a vector quantity, okay, the net dipole moment can be calculated like this: P1 squared plus P2 squared. Okay, P1 means you can consider any one of the dipole here. Okay, this minus q and this plus q. So one more minus q and this plus q. Okay, so considering this, you can find out the P1 and P2, and then you have to consider the square. Then you have to add the two squares, and then you have to take square root. This is according to the vector form. Okay. Okay. So here, what is the dipole distance between these two charges? This minus q and this plus q. What is the distance between the two charges? Can anyone tell me? You can unmute yourself and talk. Because for calculating the dipole moment, we need the distance as well. Because so in general, the dipole moment is given by one of the charges multiplied by dipole length. Okay, dipole length or distance between the two charges. So
Sir,
in
the
general,
distance of
yes,
the
yes, tell me,
distance
tell
is
me.
A, sir. A.
You are right, Ajay. That is, the distance is A. Okay, the distance is A. So now what you can do is you can write down the expression for P1. So this P1 is equal to one of the charges you can take Q into A. Okay, Q into A. This is P1. Then the next thing is P2. Okay, P2 also, the dipole distance is from here to here. You are having the distance A because the y coordinate is A here. So from origin to this charge, you are having the distance A. So here also the same distance. Okay. Now you have to find out P1 squared plus P2 squared. Okay. So the net dipole moment P net is given by root of P1 squared plus P2 squared. That means Q squared A squared plus Q squared A squared. Okay. So what will you get now? You will be getting 2 Q squared A squared. So this will be root 2 into Q into A. This is the net dipole moment. Now we have to find out the direction for this. Okay, we have to find out the direction for this. So actually in the options you have this root 2 QA, root 2 QA or root 2 AQ for three options. For options A, B and D, the dipole moment magnitude is given by root 2 QA or root 2 AQ. Okay, for options A, B and D, you have this magnitude. Now we have found out the magnitude of this dipole moment, but now we have to find out the direction as well. Okay, direction as well. So how we can find out the direction? Okay, in which direction this net dipole moment is there? Can anyone answer me? You can give it a try. We have found out the magnitude of this dipole moment, net dipole moment. On which direction it is acting now? Can anyone tell me?
Sir, I'm not sure, but is it along x-axis?
Okay, your answer is along x-axis. According to you, the option is option D, right?
Yes,
According
sir.
to you, the option is D. Okay.
Yes, sir.
Any other answer, students? Anyone else can try? What is the answer for this question? Anyone else can also give you a response?
Sir, Z
Yes.
axis, sir.
Along the Z axis. So, but it is not in the four options. Okay. That's not given in any of the options here. Anyone else? You can give it a try. No issues. Even if it is wrong, then it's not at all a problem. You can just give it a try.
Sir,
Yes, tell me.
sir, I think would be x-axis, sir.
Okay, option D. Already one student has given the answer. So your answer is also option D. Fine. So any other responses from your side, students? Anyone else? You can give it a try. Okay, now let us discuss that. So actually, what is the direction of electric dipole moment in a dipole? What is the direction of electric dipole moment in a dipole in general? I am asking. In general, what is the direction of electric dipole moment in a dipole? So you please consider this is a dipole, okay, and you are having minus q here and plus q here, okay. In general, what is the direction of electric dipole moment of this dipole? So this distance, let me consider is it as a in general, and this distance also a. Now you can answer what is the direction of electric dipole moment for an electric dipole in general. I am asking. For this dipole, what is the direction of electric dipole moment? This is the general scenario I am asking. Can anyone give it a try?
Sir,
Yeah, tell me.
sir, it is from minus Q to plus Q, sir.
You are absolutely right. In an electric dipole, the direction is always from minus q to plus q. Okay. So it is along this direction. So for this dipole, the direction of dipole moment is along this direction. Okay. From minus q to plus q. Okay. Right. So based on this, you have to find out the direction of the net dipole moment for the present problem. So here you are having minus q here. Here you are having plus q. So what is the direction of electric dipole moment due to this dipole? So let me consider it as P1. It is actually along this direction. Okay. P1. Do you understand? So for this dipole, minus q to plus q, the direction of dipole moment is from 0 to this point. So along this direction. For this dipole, for this thing, what is the direction of this dipole moment? That is along this direction. Okay. So along this direction, P2. Okay. So P1 is a vector and P2 is a vector. So the net dipole moment is actually located in this direction, or is actually pointing along this direction. So you will be having net dipole moment along this direction only. So what is the direction of this? This is along the line joining the points 0, 0. Okay, this 0, 0 and the points A, A, 0 here. Okay. Why it is so? Because P1 is along this direction, P2 is P1 is along this direction, P2 is along this direction. So the net is given by this direction. Okay. So it is along the line joining x equal to 0, y equal to 0, z equal to 0, and x equal to a, y equal to a, and z equal to 0. That is option B. Okay. That is option B is the right answer for this question. Okay. Option B is the right answer for this question. Do you all understand this, student? Do you all understand this?
Yes, sir.
Yeah.
Yes, sir.
This is how you need to solve this numerical problem. Okay. Right. Shall we move on to the next topic, students?
Yes, sir.
Yeah. So now I will be sharing you a PPT. Okay. Are you able to see the PPT? Students, are you able to see the PPT?
Yes, sir.
Okay. So last class we started our discussion on capacitors. Okay. So now we are continuing with that. So when you have a series combination of capacitors, so what is mean by series combination of capacitors? So here you see the capacitors are arranged like this. Okay, head to tail arrangement. Head to tail arrangement. You have one capacitor here, another capacitor here, and the third capacitor here. In the same way, you can arrange n number of capacitors. Okay, you can arrange n number of capacitors, but you have to arrange like this for a series combination. Series combination means it is head to tail arrangement. So this can be taken as C1. Okay, so this capacitor can be considered as C1, this can be considered as C2, and this can be considered as C3. You have three capacitors and they are connected to a battery which is supplying a potential capital V. Okay, so when you supply a potential difference capital V to this combination of capacitors in series, what happens actually is that there will be a potential drop across each capacitor. Okay, there will be a potential drop across each capacitor. So here you will be having a drop of V1, and here you will be having a drop of V2, and along this capacitor C3 you will be having a drop of V3. So there are potential drops across each and every capacitors. So the total potential V is given by V1 plus V2 plus V3. Okay, the total potential supplied by this battery is given by V1 plus V2 plus V3. So this is the total potential, and V1, V2, V3 are the potential drops across the individual capacitors. So the charge actually, due to the potential difference supplied by the battery, charges are actually flowing on this network. Since it is a series combination, the charges across each of the capacitors is same. Okay, for a series combination, the charges actually are same across each and every capacitor. So it is capital Q only, but the potential actually drops across each and every capacitor. So the total potential is given by V equal to V1 plus V2 plus V3. Okay. So you all know very well the general formula for capacitance. That is, you all know very well the general formula for capacitance. That is given by C equal to Q by V. Okay, this is the general formula for capacitance. C equal to Q by V. So here, when you want to find out the different potential difference, you have to consider V equal to Q by C. Okay, V equal to Q by C. So across this capacitor C1, the potential drop V1 equal to Q by C1. Okay, so across this capacitor C1, the potential drop V1 equal to Q by C1. Across this capacitor C2, the potential drop is V2 equal to Q by C2. Across this capacitor C3, the potential drop is V3 equal to Q by C3. So in all these expressions, the Q is common because in a series combination, the charges never changes. Okay, only the potential changes. So V1 equal to Q by C1, V2 equal to Q2 by C2, V3 equal to Q by C3. So V equal to V1 plus V2 plus V3. The total potential difference is given by V equal to Q by CS. So while simplifying these expressions, you will be getting this thing. Okay, that is this thing. 1 by CS equal to 1 by C1 plus 1 by C2 plus 1 by C3. That is for capacitors in series, you will be having this expression 1 by Cs equal to 1 by C1 plus 1 by C2 plus 1 by C3. So in this way you can find out the total equivalent capacitance for the capacitors in series. And if you have n number of similar capacitors, each having capacitance C are connected in series, the equivalent capacitance is given by this expression, Cs equal to C by N. Okay. When you have n similar capacitors each having capacitance C connected in series, the equivalent capacitance is given by this expression. Okay. So this is how you need to understand the series combination of capacitors, and I think you all can understand this concept very easily since you all might have studied these concepts. Okay, right now in your 12th grade. Okay. Now I am moving on to my next slide. So for that I have to close this annotation. So parallel combination of capacitors, you can see here. The battery is shown here. Okay. The battery is shown here. So you have the battery here, and the capacitors are actually connected in parallel like this. Okay, this is called the parallel combination of capacitors C1, C2, C3. All of them are arranged adjacent in an adjacent manner. Okay, so C1, C2, C3. Here the charges are actually separated for different branches. So here you will be getting Q1 amount of charge, and here you will be getting Q2 amount of charge, and here you will be getting Q3 amount of charge. So the total charge Q, okay, the total charge Q entering this circuit actually branches into Q1, Q2, and Q3. But the potential difference is the same across each and every capacitor. Since this is a parallel combination, the potential difference doesn't change. Okay, V. So the total potential supplied by the battery actually you will be getting across all the capacitors due to the parallel combination. So this is Q, and this Q is separated into Q1, Q2, and Q3. Okay. So now the same expression C equal to Q by V. From that you can calculate Q1 equal to C1 into V, Q2 equal to C2 into V, Q3 equal to C3 into V. So like this you can calculate the different charges. Okay. So the total charge flowing through the network Q is equal to Q1 plus Q2 plus Q3. So for that you have to add all these expressions. You will be getting C1V plus C2V plus C3V. Okay. So in this manner, the total charge Q equal to Cp into V. Cp means the total capacitance for this network. So Cp equal to C1 plus C2 plus C3. That means even if you are having n number of capacitors in parallel combination, what you have to do to find out the net capacitance or net equivalent capacitance, that is you have to simply go for summation of all the capacitance values in order to get the total capacitance. Okay, in parallel combination. If you have n number of similar capacitors, each having capacitance C, then the total capacitance is given by Cp equal to N into capital C. Okay. So this is how you need to understand the concept. And now we are moving on to the next slide. So what will happen if you place a dielectric in between the two plates of a parallel plate capacitor? What will happen? So that concept we are going to discuss a little bit here. So actually, since this is a parallel plate capacitor, okay, this is a parallel plate capacitor, you are actually giving a plus Q amount of charge here and minus Q amount of charge here. So you will be getting electric field due to the parallel plate capacitor. It is considered as E0. Okay, the field lines are passing from this positive charge to the negative charge. Okay, so this negative charge is actually the charges on this plate, and this positive charge are the charges on this plate, and the field due to this charge on the plates is given by E naught. But what happens is when you place a dielectric slab here, dielectric is nothing but material. Okay, so that dielectric is kept here, and charges are actually induced on the surface of this dielectric. Due to the presence of positive charge here, you are getting negative charges induced here. And here also, due to the presence of negative charges, positive charges are induced on this dielectric material. And due to the induced charges, you will be getting some electric field that is represented by EP, E suffix P. Okay, that is the electric field due to polarization. This is the concept of polarization that we have discussed already. And the field due to polarization is represented by EP. And due to this EP, you will be getting electric field, and this electric field is in opposite direction, as you can see clearly from this positive charge to this positive charge. Okay, from this positive charge to this negative charge, this positive charge to this negative charge, this positive charge to this negative charge, and this positive charge to this negative charge. The field direction will be like this. The actual electric field due to the parallel plates is in the opposite direction, so the net electric field is reduced, and the net electric field is given by E equal to E naught minus EP. That is, the opposing field or the field due to polarization actually reduces the actual electric field. So if the thickness of this dielectric slab is given by small letter t, okay, and the distance between the two plates is given by small letter t, what is the capacitance value, okay, for this entity, or the capacitance value for this parallel plate capacitor with the dielectric material of thickness small t and dielectric constant capital K, okay, and dielectric constant capital K introduced here, okay, introduced here. What is the capacitance value? That is given by C equal to epsilon naught A divided by D minus T plus T by K. This is the capacitance value when a dielectric material of thickness T is introduced, and the dielectric material should have dielectric constant K. So the dielectric material of dielectric constant K and the thickness T is introduced between the two plates of the parallel plate capacitor. So the small letter d is nothing but the distance between the plates, and this is the capacitance value for this arrangement. And you can also place different dielectric materials of different thicknesses in between the two plates of the parallel plate capacitor. If you have many number of dielectric materials of different thicknesses, T1, T2, T3, like that, and the dielectric constants of those materials are plus T1 by K1 plus T2 by K2 plus it goes on. Okay, so the capacitance value for the parallel plate capacitor, when you place a dielectric materials of different thicknesses and different dielectric constants, then you will be getting this equation. Okay, this is the important thing which you need to understand, or which you need to know as far as this concept is concerned. Okay, the next thing is after introducing a dielectric material, okay, what you can do is you can actually disconnect the battery supplying power to the circuit, and you can also retain the battery connection. You can have two cases here. That is, after introducing a dielectric material in between the two plates of a parallel plate capacitor, you can disconnect the battery, or you can retain the connection of the battery. What will happen to the different physical quantities in these two scenarios, or in these two cases? That has been given in this table. So the charge stored in the capacitor remains constant when the battery is disconnected. Okay, but when the battery is connected, the charges are actually increasing. Secondly, the capacitance value, when the battery is disconnected, the capacitance value actually increases due to the presence of dielectric material, and even when the battery is connected also, the capacitance value increases. Okay, what will happen to the potential difference between the two plates? When the battery is disconnected, the potential difference actually decreases. Okay, now you can understand why the capacitance value increases here, not only because of the dielectric constant of the material, but here the potential difference decreases. This is one of the reasons for the increase in capacitance value. So how it is happening? So you all know very well, C equal to B. Okay. So here when the battery is disconnected, okay, when the battery is disconnected, the charge remains constant. It has been mentioned earlier. So this charge remains constant means now this capacitance is inversely proportional to the potential difference value. So the potential difference here decreases. Okay, potential difference here decreases. Then what will happen to the capacitance? Automatically it increases because of the inverse proportionality relation. Okay, so that's why the capacitance value actually increases here. Here, what will happen to in the second case when the battery is connected? What will happen to the potential difference? It remains constant. Okay. How here also you can apply the C equal to Q by V formula. C equal to Q by V formula, the charge actually increases, the capacitance value also increases. Okay. That means V equal to Q by C. So this thing also increases, proportionately this thing also increases, so that the ratio V remains constant. That's why the potential difference between the plates remain constant in case of the battery remaining connected. Okay. Then the electric field between the plates, what will happen to that? It actually decreases when you disconnect the battery. Okay. It remains unchanged when the battery is connected. Okay. Then the energy stored in the capacitor, I think we have already discussed the energy stored in the capacitor concept. So the energy stored in the capacitor, it decreases when the battery is disconnected and it increases when the battery is connected. Okay. So these are some of the important points which you need to understand clearly. Okay. So then only you will be able to solve the numerical problems. Okay. Right. So have you all understood the concept, students? Have you all understood the concepts?
Yes, sir.
Okay. Okay. Now we will be discussing some numerical problems related to this electrostatic potential and capacitance. For that, I will be stop sharing this PPT and I will be opening the whiteboard now. So let me write down the question now. A numerical problem. Okay. So the problem is here. "27 drops of same size are charged at 220 volt each. They combine to form a bigger drop. To form a calculate the potential of the bigger drop. Calculate the potential of the bigger drop. So this is the problem. You are having options 660 volt, 1320 volt, then 1520 volt, and 1980 volt. Okay, this is the question. 27 drops of same size are charged at 220 volt each. They combine to form a bigger drop. Calculate the potential of the bigger drop. Okay. So now let us consider that. Okay, let us discuss the solution for this problem. So the number of drops, let us consider that number of drops n equal to 27. Okay, radius of smaller drop equal to smaller. Let us consider like that. And the radius of the bigger drop. Okay, radius of bigger drop, let us consider it as capital R. Okay. So now we have to find out the potential of the bigger drop. So the potential formula, what is the formula for potential? Okay. So in general, the formula for the potential is K into Q, V equal to K into Q divided by R. This is the electric potential formula, V equal to KQ by R. So in this expression, we need to first find out the radius. Okay, radius also. So here we need to calculate the potential of the bigger drop. For that, we need to find out the radius of the bigger drop, and also we have to find out the charge on the bigger drop as well. Okay. So both these things we need to know, then only we will be able to calculate the potential. Because for calculating the potential, we need this Q and this R. Okay, this K is a constant, so we don't have to bother about that. This charge on the bigger drop and the radius of the bigger drop we need to know. Okay. So for that we need to write down like this: volume of bigger drop is equal to actually 27 drops of the same size combined. Okay, so 27 into volume of smaller drop. So all the 27 drops combined, okay, and form a bigger drop. So 27 into volume of small drops. So the drop actually is in a spherical shape. Okay, that you all know very well. So that volume is actually 4/3 pi capital R cube is equal to 27 into 4/3 pi small r cube. Okay. So after simplifying this expression, you can get the radius of the bigger drop. Okay, radius of the bigger drop. So here 4/3 pi will be cancelled. R cube equal to 27 into small r cube. Okay. So capital R cube equal to 27 into small r cube. So this implies capital R cube equal to 27 into small r cube. That means capital R equal to 3r. Okay. After taking the cube root, this capital R equal to 3 into small r. Okay. So now we got the radius. Okay, we got the radius. So now we shall apply the potential formula. Potential formula. So I think I have opened the next page. Okay. So now for small drop, okay, for small drop, the potential is given by V equal to K into small q divided by R. For bigger drop, let us consider the potential V prime equal to K into capital Q divided by capital R. This capital Q is the charge on the bigger drop and the small q is the charge on the smaller drop. Okay. So since the 27 small drops combine to form a bigger drop, okay, according to the principle of conservation of electric charges, charges can neither be created nor be destroyed. So in that case, the charge on the bigger drop q should be equal to 27 into small q. Okay, because the charges on the 27 drops, okay, that will be equal to the charge on the bigger drop. So capital Q equal to 27 into small letter q. And now what we can do is we can substitute this q on this expression, and we know the capital R as well. Capital R equal to 3 into small r, that we know very well. So P prime is equal to K into 27q divided by 3 small r. So this will be 9 times K into capital Q divided by R. Okay. So this quantity 9 into kq by small r is nothing but 9 times the potential on the smaller drop. So P prime is equal to 9 times the potential on the smaller drop. In the question, they have given you the potential on the smaller drop as 220. Okay, so here they have given you. So here you can see the potential on the smaller drop is 220. Okay, so using that concept, here 9 into V, 9 into 220. So here this is 9 into 220. This will be 1980. So in question, this is 1980 volt is option D. Okay, this is option D. Have you all understood this problem, students? Have you all understood this?
Yes, sir.
Anyone having any doubt on this?
Yes, sir.
Okay, if there is no doubt, then that's absolutely nice. Okay. Okay. Then we shall move on to the next problem. Okay. We shall move on to the next problem. I will be writing the question here. So the problem, if potential in volts in a region, okay, in a region is expressed as V as the function of x, y, z is equal to 6 xy minus y plus 2y z. Then the electric field is in Newton per Coulomb. Okay, Newton per Coulomb at point 1,1,0. Yes, 1,1,0 is. So I am giving the options. Minus within the bracket 3 I cap plus 5j plus 3k cap. So option B, minus 6 I cap plus 5j plus 2k cap. Option C, minus 2 I cap plus 3j plus k cap. Option D, minus 6i plus 9j plus k cap. Okay, so you need to find out the electric field and how you can proceed with this thing. So let me give you the hint here. E equal to minus dv by dx I cap minus dv by dy j cap minus dv by dz k cap. This is the hint to solve this problem. Can anyone give it a try and tell me the answer? Actually, this is a partial differentiation. Okay, dou v by dou x, dou v by dou y, dou v by dou z. This is the partial differentiation. We have only few minutes left. Can you do it quickly and tell me the answer? You can take this minus as common. Okay, minus as common within the bracket dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap. Okay, so when you simplify here, so first of all, the entire equation, when you simplify with respect to x, you will be getting 6 I cap, then plus the entire equation you are differentiating with respect to y. Okay, you differentiate with respect to y, then what you will get? You will be getting 6x plus 2z. Okay, like that. Simplify and tell me.
Sir, is
Yes.
it option D, sir?
You are getting option D, right?
Yes, sir.
Can you recheck that? I think students, we are running out of time. Okay, so I think you have to join the next session as well. So we shall keep it this much for this session, and you will be having a test during this weekend. Okay, the portions for this test is actually the concepts of electrostatic potential, energy, and capacitance. Okay, these are the portions for the test which you have to attend this weekend. Okay, so be prepared and write the test. Okay, if you have any doubts on solving the numerical problems on that test, we will be considering that later. Okay, so thank you so much for joining this session, and we shall keep it this much this session. Thank you so much.
Thank you, sir.
Thank you.
Thank
Thank
you,
you,
sir.
sir.